everyone, and welcome. It is Wednesday, and it is a special Wednesday. It is the third episode or third part in our group classification. This has never been done before, and we're so happy that we have Daniel Sheikh, classifier to the stars, on board for this project. Basically, a group project for all of us. We actually literally get to go through the entire classification process with Daniel. So the first one, you remember we were in the lab taking the actual readings. The second episode, we were getting those readings from the software of the SEM into a more portable Excel file. Now we're going to be working with that. We actually cleaned the data. Now we're actually going to be getting the data in a submission form to the nomenclature committee. So like I said, this has never been done before. I'm absolutely loving it. So Daniel Sheikh, thank you for joining us with this one. And I do have some news. We've changed the name of the playlist on our YouTube channel. It used to be From the Lab, and we had other scientists in there. Well, we kicked them all out. Now it's From the Lab with Daniel Sheikh. So you have your very own playlist, buddy. Welcome to the show.
Thanks so much. Thanks so much, Topher. Really appreciate it. Yeah, this is going to be a very exciting segment, indeed, especially the third part, since we're for the first time, I believe, ever going to see the actual submission process to the nomenclature committee of the Meteoritical Bulletin database for a sample, which I think that basically adds full transparency in itself into the entire classification process. So really excited for that.
Yeah, I'm glad you pointed out because this is people ask like, what do I need to do to get a rock classified? And they think it's just snap your fingers and it's done. It takes a lot of work, a lot of time, and a lot of dedication by someone who has the machine and the know-how, obviously. But then it's a standard procedure. There's no magic. There's no Harry Potter going on behind the backgrounds. It's literally just a following of steps, and any scientist that does it the exact same way. So we're looking behind the scenes here, what happens to every single submission. But we're doing a little extra on ours because we're special. um, I'm actually gonna turn it over to you. I have a few slides here. The crew we've been looking at the outside of the stone because there's going to be a part in the submission where we have to explain or describe features we see on the exterior of the stone, uh, interior slices, any features like that catch our eyes. So the crew has already looked over these pictures in detail. I just wanted to flip through them real quick so our viewers can take a look at them. But this is the main mass, and it is no longer going to be, oh, Pat Slice, uh-oh. It is no longer a whole stone. These are the only pictures ever in existence of it as a main mass intact. Um, Now, Sue is in the middle of editing these pictures right now, but I wanted to point out some interesting things that we saw on some slices, and then I honestly, I'm going to turn it over to Daniel, I promise. But this is Pat's slice, the unpolished side, and I just wanted to point out some things that we're going to be talking about throughout this conversation. These shock lines, these shock veins that go through every single slice in the exact same formation. Plus, if you notice up on this top, we have some discoloration. I'd like the crew to be able to talk about that. Um, in here is a big metal bleb as well. I think Marissa's slice has the biggest metal bleb there is in any of these. So we're going to get a measurement of that for you as well. Most slices are really homogeneous. They all look pretty similar. So these are very representative, but every single slice is going to have these shock veins going all the way through it. And as we learned last time with Daniel giving us the classification, he hinted at an S5, so a shock level of 5. Daniel, oh, there's a close up of that discoloration area. Um, could it be secondary lithology? Could it be weathering? Questions. All right, over to you, big guy. Thank you very much.
Okay, so before I share my screen, so just so everyone's up to date. So if you remember from part two, we took the data from the instrument software and we put it onto an Excel spreadsheet. Now, once the data is on an Excel spreadsheet, that doesn't necessarily mean that it's all ready, just to submit right away. We still have to do some data cleanup, a bit of data processing. But the good thing, at least, about that is that once it's on the spreadsheet, we can look at every site that we looked at and we can see exactly what specific minerals we have and what their compositions are. Then I have several charts that are going to help with the classification process. For example, what type of chondrite we have, what shock stage, what weathering grade, things of that nature. And then, of course, I have the Meteoritical Bulletin official submission form Excel spreadsheet to submit our sample on. So that's sort of the approach I'm thinking we'll do. And then probably at the end, we'll probably navigate between the submission form, the data sheet, and also the form that has the history information. And of course, if anyone wants to add anything into the physical characteristics of the specimen, like from what we're seeing from all the samples and the images that Topher is showing, feel free to do so. It would be great to have this sort of just a discussion, more of a conversation, rather than me trying to just talk over doing a lot of data processing. So happy to answer any questions. We happy to have any kind of discussion while the data processing is ongoing, but I'll make sure to explain a little bit into some of the important things that I'm doing in the process.
Fantastic. Putting the group in group classification. This is Marissa's metal bleb. So yeah, Marissa has the biggest metal bleb in her piece. So I will measure that so you can submit that, Daniel, while in the background while you guys are talking.
Definitely. And also, if anyone notices if you notice any chondrules in their Topher and you want to get just a rough estimate as to the diameter for a few of those, feel free to measure those as well. I did get some measurements, or I do have some images of some chondrules from the sample, and I do have a scale bar so I could get some estimates on what their diameters are as well. I don't think it would be too useful for this particular classification. There are some specific kinds where you definitely want to get chondrule diameters, but it's a good practice to just include a few of them in there as well, or at least if we see a few chondrules, just say that we found a few chondrules in the sample. As you can see, it's really hard to sort of pinpoint many chondrules in this sample, and
Yeah.
it's sort of very equilibrated, is what the term that we tend to use for this.
All right. Those are them. All right, man. I'll let you share whatever media you want to share, and you're on your own.
All right, sounds good. Okay, so while everyone's adjusting to all of the data and numbers that sort of appears on your screen, let me just say that this is the data after we've processed it onto the Excel spreadsheet, but it's nowhere near complete. We now have to actually do a bit more processing here. So just to show everyone what these different tabs are on Excel. So this first tab is called data. So what you're seeing are various columns here. This first column is just labeling each of the spectrum. This again just represents every time we took a spot, an EDS spot on one of our locations in our sample, it marked a spectrum, and it goes from 1 to, I'm just going to go through it,
66.
goes to about 66 different spectrum that we took. And this is only useful if we're trying to just pinpoint a particular spectrum and find out like where we took it, if it has like a weird chemistry to it or something like that. So it's good to have labels. These columns all right here show different elements. So for example, oxygen, sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, potassium, calcium, titanium, chromium, manganese, iron, and nickel. So quite a large amount of elements, but these are all very important elements given that different mineral phases can have significant contributions from each of these elements, which we pick up with our X-ray detector. And the total just means everything is sort of normalized to 100. I'm measuring these all using what's called molecular percent. Sometimes you hear it in the literature as atomic percent, basically we're looking at different moles of each of these essentially elements in our sample. And this is important when you're trying to get certain calculations for defining meteorite groups. Then the last part just shows the what's called the project pathway. So this essentially just means where we were. So you'll notice I have, for example, site 1 zoomed, site 2 dark blue. You're probably wondering what these means. These corresponds to those different locations on the thin section, which is right here, that were some of the sites that we visited to get some of the data. So for reference, this tab right here is site 1. This is the red dot, so this is right here. So we have, of course, our zoomed out images right here. And then, of course, when we zoomed in right here, we did get a few spectrum points. You might not be able to see them at this magnification, so I'd probably have to, blow up, do something like this. But even if you can't see them, just know that the spreadsheet is available. So if you want to take a closer look at them, you could. But you can see we have Spectrum 1 right here, Spectrum 2, and several other ones. So I might be toggling a bit back and forth between this data tab and different sites, depending at the spectrum that I'm looking at, if I want to like check where it's at.
That's
So,
amazing.
sorry, go ahead, Topher.
No, I'm just saying that's really amazing and very cool that we can do that. I want to pay attention because on like the eighth row down, whatever, there's one with the nickel
Mhm.
and iron in the 40s where it's nowhere else. So I want to see where that one was taken. Yes,
Yes, yes. Okay, we'll get to it. Absolutely.
I'll be
Okay.
patient. Sorry.
So site 2, we went to this dark blue area and we really zoomed in. So this is inside one of those shock melt veins that Topher was showing earlier. That the sample has some really incredible, large shock melt veins that propagate throughout the entire sample through many slices. And so this is a nice area inside one of those veins. Now, just to keep in mind, we might have the presence of what we call high pressure mineral phases or polymorphs of some of the more common minerals that are in the sample. And for the classification, just we don't necessarily need to give their data or composition. So I won't be focusing too much on anything in the veins, given that what happens inside the veins may not be representative of the total of the rock. We call it disequilibrium processes that occur in these shock melt veins, where the pressure and temperatures are just so high that the thermal history in these areas is way different than what the entire rock experiences. And what most of the rock shows is what we call an equilibrium, thermal history. And so that's what I'll be focusing on. So
Hmm.
these are good to just see like what kinds of minerals we may have in here, but not necessarily need to be reported in the write-up. Then, of course, we have a few other sites. So we have site 3 here. So this is between the dark blue and the purple point. So we're somewhere in the middle here. Well, I don't know if it's this one or this one. I think it's this one, but we're
Yeah.
somewhere in the middle. So you can see. And then site 4 is the yellow dot right there. Site 5 is the light green dot right here. Site 6 is the light blue dot right here. And just rounding off, site 7 is the dark green dot right here. You'll notice I have an area that's called site 11. This was just a zoomed out image I took
Hmm.
somewhere on the sample where I saw there were a lot of chondrules. So you can see these rounded images here. And I just wanted to capture just a few of them just to show that it has a overall chondritic texture to it. But basically, those are all the sites. So I'll be going back and forth between the data and these sites. And then once we have the data that's organized and we know what sort of minerals we have in their compositions, I will then go to the final tab, which is right here. And this says chart. And I have several charts on here that are of interest because we're looking at an equilibrated ordinary chondrite, meaning an ordinary chondrite where the mineral phases are very similar in chemistry. This diagram is going to be very important for separating HL and LL chondrites. And then these other diagrams correspond to tables that are taken from very important research papers in the field of meteoritics that actually are important to the nomenclature of ordinary chondrites specifically, but also chondrites in general. So Venchmussen-Wood is of 1967 is a very important paper because it actually was the first major paper to separate the chondrite groups according to their petrologic type. So from 1 to 6, where 3 is the most primitive, and as you go to 6, that means increasing amounts of metamorphism due to heat on the asteroid. And as you go down to 1, that indicates increasing amounts of aqueous alteration. Stoffler et al. 1991 is a very important reference because this discusses shock deformation effects that you see in specific diagnostic mineral phases and ordinary chondrites. This is all assessed using a petrographic microscope or a polarizing microscope. So we don't have the specific, images of those thin sections here to show, but I have looked at the sample in thin section. And there are a few tricks you could use as well, using some of those images from several of these sites that can also fit into here, whether or not we see certain mineral phases. And then finally, this is the weathering scale for ordinary chondrites by Walatzka, and this is from 2005. And basically, this just
Hmm.
has to do with when you're looking at the thin section, whether or not you see oxidation or rusting of metal, and whether you see other phases that are being altered, like silicates. There's other scales as well with Antarctic meteorites where they just look at the entire sample and they assign things like A, B, or C. And then, of course, some people just look at the hand specimen and they try to see if the fusion crust is weathered, and they come up with their own scale. Normally, this is sort of the approach to go. It's normally done on the thin section, and I already sort of got a weathering grade of this, but we can also look at the sample, like the hand specimen, and also try to see whether or not we can see similar things there as well. So that's basically it. And then once we have the data all processed and we sort of know what ordinary chondrite group we're dealing with, what the petrologic type, shock stage, and weathering grade are, we'll then go right into getting that submission form made to the METBOL. So if that sounds good with everyone, I'll just get started on showing how we go from all this messy data to a bunch of clean and processed data. So unless anyone has any questions right now.
I just had one comment. You can continue doing what you're doing. It's amazing that the touchstone papers you're using to aid you in your classification are 91 and 1967 is the oldest. Like it's a young science. At least the classification of them. Good
Yeah,
job.
there's a, I mean, there's a saying that if the overall trend in the system is good, to, that it's consistent and it has worked, even up to recently, there are, of course, many papers out there that are trying to create a new system, or at
Mhm.
least changing some parts of this existing system, which, some of these criteria probably don't hold very well today with what we know. But the overall idea for some sort of system like this tends to fit the trends that we see in
Yeah.
in ordinary chondrites from 3, 4, 5, and 6 petrologic types. So
Mhm.
it's not perfect, and obviously there's many things that are outdated in several of these schemes, not just this one, but these two as well. But they're good for anyone who's trying to just trying to just understand what is the best introductory,
Mhm.
paper that I should read if I want to learn about petrologic type or shock stage.
Yeah.
And these are
Agreed.
all relatively simple to read compared to some of the papers that are out from the past few years. Okay, so if there's not any other questions, I'll get started. So the first thing that I do is, well, there's a few things I do. The first thing I do is I get rid of this little thing that shows the statistics. This is averaging everything, but we know we have different mineral phases, so we have to separate them out according to mineral phase. So I get rid of that first. The next thing I do is I need to create more columns, because while it's great to see, each of these elements on here and what their atomic, proportions are, I want to have important things like, what is my phaolite of my olivine? What is my ferrosolite of my pyroxene, etc. So I'm going to create a few columns here. Another thing that I tend to do is I want to make sure that my mineral phases have the correct stoichiometric formulas to them that fit with what you'd expect, in principle. So for example, when you look at something like a orthopyroxene, you might see something that looks like this. You might see, MgSiO3. That's like a enstatite, which is a magnesium, rich orthopyroxene. You might see something like Mg2SiO4. This is, forsterite. This is the magnesium-rich olivine. in these chemical formulas, you'll notice that there are 3 oxygens in the pyroxene and 4 oxygens in the olivine. And when you add up the cations, which are the magnesium and the silicon, in a pyroxene you get a sum of 2, and in olivine you get a sum of 3. And whenever you collect data and you want to make sure you have a clean mineral phase, you want to make sure that you get cation sums that add up to what they should be. If you get anything different, then you either have some sort of contamination, which can be a result from things like weathering, or you have 2 phases that are mixed, or you don't have a stoichiometric mineral per se, which may indicate you have something else that doesn't necessarily give the best data. So we want to make sure we have clean data. So what I always do is I do cation over 3 oxygen. So this is looking at the amount of cations I have over my total oxygens, and I'm going to do this for both 3 and 4. So this column is going to check to make sure I have clean low calcium pyroxene totals, and this column is going to check to make sure I have clean olivine totals. So that's the first thing I always do. I want to make sure I have good olivines and good pyroxenes. Then the next thing I do is I'm going to make a few more columns here, and we're going to look for those important parameters, the phthalate, the ferrosilite, and the wollastonite. So this comes from the olivine, the phthalate, the ferrosilite, and wollastonite come from the low calcium pyroxene. And these are important for the classification. And these 2 numbers are very important for deciding whether we have a HL or LL group equilibrated ordinary chondrite. Okay, so these are basically what we're going to be looking at here, these 5 numbers right here. And so the way we start is we have to calculate the cation sum. So the first thing I do is I take 3 and I multiply it by the sum of all of these cations right here. And I divide it by the number of oxygens. So I get a number like this. And then I do the same thing here. So I'm just gonna make it easier. You'll see I'm gonna do sort of a lot of copying and pasting. In some cases, it's just a little easier to do that. And I'm gonna repeat that for all of those. And then here, we're gonna calculate the phthalate. So that's just the molar ratio of iron divided by the sum of iron plus magnesium times 100. Then we're going to do ferrosilite, which is just iron over the sum of iron, calcium, and magnesium times 100. And then wollastonite is just calcium divided by calcium plus iron plus magnesium times 100. So you can see these are all we're going to focus on, just these components right here. And I'm going to bring this down, and it's going to go for all of them. Now, clearly, not every spectrum that we got is an olivine or a pyroxene, but I'm just bringing it down anyways. And and what I'm doing this is so I can filter out the olivines and the pyroxenes from everything else. And then I can just focus on those 2 mineral phases, which are really all we need for the classification of a equilibrated ordinary chondrite. So I have 2 decimal points for my cation sums. That's because I want to be as close to the correct stoichiometric values as possible. And I have 1 decimal point for my phthalate, ferrosilite, wollastonite. This is just because with the detection limits and the errors that we have on all of these data points that we collected, it's normally good to the first decimal point or third significant figure in this case. So this is why I'm putting them with 1 decimal point. You might see sometimes some people report them with 2 decimal points. If you're doing something like electron microprobe, or you're doing something like laser ablation, and you're looking at very you know things with greater detection limits and much more spatial resolution, you can go to the second decimal point. Here I always just stick to 1, which for the classification 1 is actually pretty good as well. So now that we have this, the next thing I do is now I filter out all my spectrum according to the cation sum. So what I'm actually going to do is I'm going to combine all of the different sites together. So there's the approach where I could take each of the sites and separate them out, and then I could see how they all compare. And then the other approach is I can combine them all together. So just for fun, I'm actually going to do both approaches here. So I'm going to copy this, And to make it a little neater, I'm actually going to put it on the sites that they're currently on. So that way it's all in one location. So
Yeah.
from one site, we have the data and we have, the images. And so I'm going to do this first for all the different sites so that we have them all in order. So if anyone wants to talk about something in the meantime or has a question, now is a perfect time.
Pat, I know you have a question, and you haven't put your hand up. You haven't interjected. It's an open mic night, man. There, your hands up. Congratulations. This is the
Yeah,
this is the
so
part of the group thing, so everyone's welcome to interact.
yeah, so this is really interesting, and Topher, you mentioned the possibility of multiple lithologies, so it's easy to see that this is a path towards understanding if we have multiple lithologies.
Art?
When we were viewing the slices, it seemed like all the metal blibs were surrounded or bordered by what looked like alteration of possible metal sulfides or a different form of the iron, because the metal blibs, all of them, are super shiny, and it doesn't look like the shiny metal blib has been altered in any way, but all around it, the outside of it looks like alteration of metal sulfides or different iron in there in the slice.
Yeah, I
Yeah.
think those are oxides. Sorry, Daniel.
Okay.
No. Go ahead, Pat. Go ahead. No worries.
Yeah, so I think those are oxides, and they're sometimes talked about in the literature as rust halos.
Mm-hmm.
And it's just like, when you have a bolt that's laying in a mud puddle, the outside of it is going to rust, but the inside doesn't. And one important tidbit that leads to is that meteorites are surprisingly porous. And so on exposure to water, that water wicks down into the grains of the meteorite, and you can get oxidation of the metal grains, and it starts at the outside. And many of these stones from Northwest Africa have been in the desert environment for quite some time, and so it doesn't rain very often, but when it does, it's a lot. And so even a few of those over the decades could be enough to create those rust halos around the metal grains.
Thank you.
Yeah, there's certain ways that you could actually observe, the weathering in metal pretty cool, like up close using chemical data. So like if you analyze a metal, there are certain features you'll see during weathering. The first is that you're not getting a clean spectrum, so you're not seeing, just iron and nickel. You start seeing oxygen, starting to show up, and then you see things like silicon, and then you see, some of your totals drop off. So chemically, you can actually see, weathering, iron hydroxides in altered metal. And the other way you can check is using some of our images right here. So I don't know if you can see it, but this is this is yellow, this is a troilite, and then this is a metal, this blue right here. But right on this upper right edge, you'll see the color is a bit faded, and you'll see here it sort of looks more gray. That's clearly a sign of weathering of the metal. You can see this is an oxidation process there. Okay, so we're just about done. Let's just go site by site and just see how the data looks. So what I first do here is so this is site one. So this was Topher's red dot right here. This was his site right here. So we'll start with his. And I take the data, and the first thing I'm going to do is I'm going to organize it and filter according to this row right here, this cation over 3 oxygens here. And so that would be column T. Okay. And then now, once that's done, we can now look at everything in here. So let's take a look. We don't have to go, on every sample spectrum by spectrum, but for example, let's start with the first one. So you can see it's got, let's see, if we just look at it right here, it's got a lot of sulfur, a lot of iron. Because it's in atomic percent and not weight percent element, the oxygen in here is just going to show, even though we know that this is this mineral phase is a sulfide, so it shouldn't really have oxygen in it. It just reports that there's oxygen. But for all intents and purposes, what I use is that I see there's a lot of sulfur and a lot of iron. They're almost in, a 1-to-1 ratio, which is expected for a mineral like troilite, which has chemical formula of FeS. So you'd expect these to be very similar and like almost the same. And then this is spectrum, so we could even see which one it is. So this is spectrum 9. So if we go here and we see where spectrum 9 is, and let's see, it's going to be right here. So I'm not going to do this for everyone because it's going to take a while, but you can see it's right on this yellow spot. That is a troilite. So you can see that's what a troilite would look like when you get the composition. We can see spectrum 8 is a chromite. So I would expect there to be a large amount of chromium in there. So we can just quickly take a look at that. So spectrum 8 is here. We can see we have a little bit of magnesium, aluminum, very little silicon, and we can see there's a little bit of titanium and a lot of chromium and iron. So this is typical of something like a chromite, where in a typical chromite you get something like this. You get FeCr2O4. And so if you sort of look at the proportions, if you add chromium and aluminum together, that should equal twice the amount of iron and magnesium together. And then there'd be 4 oxygen per that. So your total cation sum should be about 3. And that's what we see right here. So we have a pretty nice chromite. Obviously, we're not going to use it in the classification, but this is kind of what we do when we see mineral phases. We try to see like, what mineral does this correspond to? Or what mineral does that correspond to? So this would be a troilite. So I can put, mineral phase here. And then, we can go one by one. So this, I'll just say what this looks like to me. This looks like a sodic feldspar. So feldspars, of course, in ordinary chondrites tend to have a lot of sodium, not very much calcium. And this is sort of what it looks like. So I'm just going to put feldspar here. Then we start going into a bunch of areas that have a cation sum that's near 2 here. This is what we typically see in a pyroxene, but we can see that 3 of them are similar, but one of them isn't. And for that, we can look at these 2 columns right here. So you notice that 3 of them have very low elastonite content. These are low calcium pyroxenes, and one has one that's very high at 46. This is a high calcium pyroxene. So that would be that red spot that we hit right there. For classification purposes, we only care about low calcium pyroxenes. So I'm just going to mark these as blue, and we're not so much focused on that red one right there. And then finally, we have the olivines to look at. So olivines, if we assume 4 oxygens in a stoichiometric formula, would have cation sums of 3. But I also said that chromite had one of 3. So we have to separate the olivines from the chromites. And the way I normally do it is I just filter by the chromium content. So that would be, column O. And then it just filters them out. So then I look at these 3 and I say, okay, they have a lot of silicon. They look very similar, almost near identical in the, the amount of each element. And then I look at their phalite numbers and they're very, very close. So this is, this is olivine and it's very equilibrated. So basically we have the olivines, we have the pyroxenes, and then that final point that Topher talked about was that metal. So that was spectrum 10, which was right here. You can see we analyzed blue, which means it iron and nickel rich area. We can see it's got a lot of iron and a lot of nickel, so this is typical of metal. It depends. You can have, of course, chemicite or taenite, where the amount of nickel in the metal varies. Usually you use weight percent element, not atomic percent element, so I can't exactly differentiate between both at the moment, but I can at least tell you that this is, iron nickel metal, and it's definitely meteoritic in composition. So basically we have the key thing that we get out of this is we get the pyroxene and olivine chemistry. I always look at the images again to see that, this olivine, which is this bright blue, is all the same color everywhere. So it looks pretty much, homogeneous in composition, which is, makes sense why this would be all the same. For the low calcium pyroxene, which is this dull green, we can see that it's very similar, and this one right here, and the ferrocite and wollastonite content, so it's also equilibrated. Based off of the texture right here, I'm not seeing evidence of zoning. I'm not seeing evidence of, different chondrules that have different chemistries, right? And I'm seeing very large feldspars, right? This is the purple. And that is, feldspars that are, on order of, some of them, reaching larger than 50, 100 microns in size. So this is clearly what we call an equilibrated chondritic texture. This is a very nice example of that. And so just from seeing this, I can tell right away that I likely have, an equilibrated meteorite. And, I can get these values right here. So I can go olivine. And now we're going to get the phalite value from this site. So I would hit average. I would get the average right here. Then you oftentimes see a standard deviation associated to it. So this is the error. This is what's called one standard deviation. So I'm just looking at, this for this, I'm just measuring one standard deviation. Then I'm also reporting minimum values. So this would be the lowest, phalite value, and then the maximum, which would be the highest. You can see they're probably very similar. And then the last thing I report is just the number of grains. So you can see here it's 3, so it's not that many, but remember, this is just from one site. And then I would do the same for the low calcium pyroxene. So you can see there's a lot of, just processing involved with this. And I do have a few shortcuts for speeding things up so it doesn't take too long. So we have the olivine phalite, we have the pyroxene, ferrocite, and wollastonite values right here. We have the average, standard deviations, and we can tell from the sample that the feldspar looks fairly coarse and the olivine and pyroxene are homogeneous in composition. So even though we're looking at one site, I'm just going to navigate very quickly to, to the first site that we have right here, and this is the chart. And so if we were to take this image and bring it here, we would look at the phalite, so it's 25.2, so I'd put this right here somewhere, and the ferrocite is 21.3, which would be somewhere here, and we're clearly in the L region right there. So looks to be L. We then can look at the feldspar being very coarse. It looks to be, so this is a scale bar for 250 micrometers, so 50 would be maybe, let's see if that's about half, and that's about a fourth. A fifth would probably be a little smaller right here. So 50 would be something like this. We could see that a lot of these grains are larger than 50 micrometers in size. And when we go to the classification of the petrologic types by Van Schmoes and Woods, we can look at some of the criteria. So some of the things I look at are, for example, the homogeneity of olivine and pyroxene. This is a very important criteria. They're relatively uniform in composition, so we know we have a 5 or a 6. The degree of development of secondary feldspar. So that is the feldspar that we see in our sample. How coarse is it? And we can see right here that it is, clearly they're large grains. Interstitial means that they're between other phases or between chondrules. In which case here we don't really have a specific chondrule we're looking at. We're just looking at between olivine and pyroxene. We can see we have some large feldspars. Let's see if they have the sizes of the plagioclase. Okay, so they don't have them listed on here, but typically for a type 5, you go from 2 to 50 micrometers for the feldspar, and a type 6, it's 50 plus. So clearly we have pretty large feldspar. So I'd say we're more consistent with a type 6. So this all sort of points to L6 from this site. Now, this is just one site. Obviously, we have to go to other sites because we're just looking at one small area in a very large thin section, right? So this is why we go to different sites and get points. But it's important to at least see that from this area, this is what the sample looks like initially. And from looking at other areas, we'll now see if this L6 classification still holds up or whether or not we have to maybe modify this. So then we go to the second site. Now this site, I told you that it's inside of a shock melt vein, so it's not going to be exactly diagnostic of, representing the equilibrium conditions of the entire rock. So I am going to skip this, but I will leave the data here if anyone wants to look at it. But I will say that if I just, very quickly just sort this by, let's say, the column. So I'm just going to look very quickly just to see if there's anything maybe interesting in here. Let's see. So spectrum 18, 13, and 14 look potentially interesting. Particularly, let's say these, either of these two. So let's just look at 18 and 13 really quick here. So it looks like 18 we took from this grain right here, and then 13, oh sorry, 18 was taken here, sorry. So this is 13, looks like. Let's see. Yeah, that would make sense. So 13 would be something like this. So if we look at the composition, it almost resembles that of a pyroxene, but there is significant amounts of aluminum in there, and there's a little bit higher sulfur. So it might not be a clean analysis, but this might be potentially a high pressure polymorph mineral phase like a meteorite garnet. So, meteorite, pyrope, this is a high pressure mineral phase you can find in shock melt veins in highly shocked ordinary chondrites. So I wouldn't be too surprised if that's what it is here. It has a very similar texture to that, but this isn't necessarily relevant to the overall classification of the rock. But if you're doing research, it's always cool to see that you might have some weird mineral phases here. So that's sort of how I look at those. Now we're looking at this area right here, so between dark blue and purple. So we're either here or we're here, but we're somewhere in this region. And we can just look at the texture and comparing it to site 1, and you could see, very similar texture in terms of the olivine looks to all be the same color. So it's probably the same composition. Same with the pyroxene. Very coarse feldspar, once again, that's greater than 50 microns in size. We have very large troilite, very large chromite, very large metal. This is all thing. And we have calcium phosphate, which is the orange. These are all diagnostic things you see in very equilibrated chondrites, where we're growing we're coarsening the grain size of these metals, sulfides, and we're forming phosphates and chromites and feldspar. And this is a typical equilibrated chondritic texture. And we can just check very quickly, once again, just by looking at some of the sites here. Okay. All right, sounds good. Okay, so we can see that from this data right here, and let me just check one thing very quickly to make sure that it's consistent. So okay, so all right, so we can look again at the olivines. And let me just check, sorry, just give me 1 second. Let me just check something right here. Okay. So it looks like the abundances of the elements that it's showing up right here for silicon for this particular sample, which is interesting, it's not quite at the exact value I would expect it to be. So silicon, normally I expect it to be lower at about 14 for olivines and near 20 for pyroxenes. I'm noticing that it's a little higher on these sites compared to the first site. Right, so you can see right here it's 14 and 19. So I'm going to go back and double check, with the data to make sure during the processing there wasn't anything that could change this. Sometimes when I do the processing, if there's a correction involved that can actually affect these numbers. But what I tend to notice is it doesn't affect these numbers so much. So we can still, assign phthalite and frostolite values to olivine and the pyroxene. They just won't look, they just won't have very good stoichiometric totals. So what I will do now is I could still look at what would be a typical olivine, and that would be something like this. And the pyroxenes would be something like this, even though the data here is a little bit different. But the key thing here is that the frostolite values are also, overlapping or very similar to what we had from, the first site right here. So you can see 21.3, you can see here they're, 21.3, 21.4. So basically the compositions are very similar. For the olivine, it's a similar thing. We look at the phthalate, and we could see, overlapping again with the first site. So that's all good. So that means that, it's equilibrated in, same composition here and here. So that's a good sign for an equilibrated chondrite. Let's then go to, site 4. Let me just sort and filter this again by column T. Okay. We can look again. We have another pyroxene right here that has a good cation sum right here. So this is a phthalate frostite 21. So that again is pretty good for a pyroxene. And then we have a clean olivine right here, and that is 25. So it looks like we also may have hit some other areas in this sample. I believe we hit near some of these veins, as we can see some of those sites. And it looks to me like these are probably olivines that are probably from within the vein. And so their numbers are a little messed up here. I think that correction factor is applied to some of these, but they also have, similar phthalate values as well. The one thing that is different is you'll notice this one right here is, a little lower than the rest. And I believe that this was, let's see, spectrum 29. So if we zoom in here, we can see it's this grain right here. And what we tend to find in shock melt veins is that sometimes these areas are heated during the formation process. And if they're left hot for a significant amount of time, you can actually re-equilibrate the composition of this grain with the surrounding melt. And that can lower it or raise it. And we could see that the value here was lowered. So if I'm doing a calculation of average phthalate for the entire sample, I wouldn't necessarily include this grain in it because it's not representative of the overall texture. It's from a melt vein. Same with maybe a few of these other olivines right here. But you can see overall, the phthalate still tends to be consistent with an L chondrite right here. And let me just check. Okay, so site 5 was the light green. We could see again, olivine, same color, likely same composition. Let me just quickly just sort this one more time. And so these are pyroxenes right here. And we can see ferrocylite is very consistent right here. We maybe have this one point right here. So that would be spectrum 41, which it might be slightly different, but we can see that the other three are very similar. And then for the olivines, which are right here, again, they are very similar in the phthalate values, which fits with the other samples. So far through 5 sites, we've found that the olivine and low calcium pyroxene are basically the same composition. We can then go to this next site, which is the light blue right here, and we can see a similar texture. Olivine, same composition. Pyroxene, same composition. Maybe there's a little hint of zoning in here and these pyroxenes. That could be what this little dark part is, but it could just be, contamination from the carbon coat, which is sort of causing these dark spots. The feldspar, though, which is interesting, you'll see that the grain size varies quite a bit from one part to another. And in this case, it makes distinguishing between a type 5 and type 6 chondrite a little tricky. So, I tend to look at the average, grain size of the feldspar across all the sites. So if we go back to, we can't really see it very well in site 5, but in site 4, we can see it's still, relatively coarse, although maybe here it's a little different. Site 6, it varies. I'd still probably be more consistent with a type 6 over a type 5, but this is all sort of what comes down to, a bit of decision making on the classifier's part, whether there's enough of the big feldspar that you measure or at least image to say it's more of a 6 than a 5. But at the same time, let's say I only looked at this one site and I didn't look anywhere else in the sample, I might think more 5 than 6. So this is the importance of getting sites in many different places in your sample. And the last thing I'll do is just look at site 7, which was the dark green, which was here. Again, we're near some kind of opaque shock melt vein that's passing through here. But we can see, on this side, we might have some small feldspars. This might have been from a chondrule, potentially. It has a lot of the high calcium pyroxene in here too. It has a similar shape. But then we have all this coarse feldspar here. And the olivine and the low calcium pyroxene are all the same color. And if I just check just to make sure, one final time, whether or not they're the same composition everywhere else or whether they're the same, that would tell us everything we need to know. So I'm going to sort and filter by the same column again. Okay. All right. And let's just take a look right here at these pyroxenes right there. And we can see that the ferrocite is basically almost the same as everywhere else. And look at the olivines. And yeah, these also overlap. Maybe this one is a little bit higher, but it might be closer to the shock melt vein, right? So sometimes you see like a specific one, like why is this one higher than the rest? So we can sort of look at it in a little bit more detail. So that's spectrum 63. And so if we just look on here and we say, why is that one, a little higher? We can just take a look around the sample. One of the downsides of taking, of course, all these images and putting them in is that they make the spectrum boxes just so small. So it's like you really have to zoom in. So we can see it sort of right here. It's not near the vein. So 58, I would expect to be similar because they're from the same olivine grain. And so if I just go back to 58, that's right. Where is it? Right here. And we can see that this one is 25.2. So that grain may, because it's very large, it may not have fully equilibrated with all the other olivines. So there may have been some zoning that was remnant, but it's still small enough where, if you average everything, it's still equilibrated throughout the sample. So my overall conclusion on this sample is that the L6 classification holds throughout the sample. And regarding the shock stage and weathering grade, so one of the key things to know about this Stauffer et al. Scheme is that you primarily are looking at thin sections in cross-polarized light using a petrographic microscope. So I looked at the sample, and there are a lot of melt veins in the sample, right? Which typically tells us that we're probably at a higher shock stage. You can also look at the olivine and to assess different criteria for how it behaves as you're rotating or stage in a petrographic microscope. We call this going to extinction, where we're taking a grain and we're assessing changes in it. The key thing to note is that I did see evidence of this thing called mosaicism and planar fracturing. All that means in mosaicism is that the grain is so deformed during the shock deformation process that you actually have different domains in the grain that behave differently when light passes through them because the crystal structure is so warped, and that creates this effect. Planar fractures just mean that if I'm looking at, an olivine, and you can actually see these using these images, is that you see all these parallel lines right here, or some of them that run this way, some run this way. We can look at, let's see if we find another area right here. Usually you look at this the petrographic scope, but you can kind of see these a bit in this sample right here. These are kind of trending northeast. And usually you have to look at the larger olivines. We can see them in a few, but when I looked at the thin section, I did see a lot of them. That's also indication of, moderate shock deformation. But the fact that we see a lot of these shock melt veins in the sample told me that we're definitely on the higher end, so at least an S4. But what took me to deciding on S5 for the classification was the presence of mascalinite. And the way you can tell this is during shock deformation, as plagioclase in your sample is heavily shocked, it becomes amorphous and turns into a glass. And because it turns into a glass, the texture of this glass is going to be very smooth. And so as opposed to these olivines and pyroxenes that have all these fractures in them, when you look at this feldspar, this dark area, you can see it's very smooth. It's relatively smooth, not a lot of fractures. You can even see there's a little bit of other minerals in the feldspar, almost like they're entrained. This is what you typically see for maskelonite, very smooth feldspar. And the other way you tell you have maskelonite in your sample is when you look at it using the petrographic microscope, you cannot see the feldspar in cross-polarized light. It's basically extinct. This is because glasses, are isotropic and you just can't see them. So it's a very useful criterion to see, but you can also tell using these images that our feldspar is, it looks very glassy. Let me use these images right here. They're a little easier. There we go. So you can see right here, it's glassy. You don't see a lot of fractures. Like you see a lot of fractures in olivine, but not many fractures in here. What this tells you is that this event that heavily shocked the olivine and formed all these fractures and deformed it was the same event that probably formed this maskelonite. So the feldspar probably was heavily cracked and then it turned into a glass upon cooling. So this tells us we're at, and the fact that we see this in different parts of the sample means that it clearly occurred everywhere. So this fits with a S5 shock stage. The only way we could be higher is if you have a presence of, for example, ringwoodite, which is a high pressure polymorph of olivine that you tend to see in shock melt veins. The best way to see this is using the petrographic microscope. You'll tend to see blue or green, olivines in plain polarized light. I didn't see that when I was looking at the sample, so we don't appear to have this phase. And if you go even higher than that, you just completely melt the rock. And what happens when you melt the rock is you lose your chondritic texture. So you can see right here, this doesn't really have a, much of a chondritic texture, but we're in a vein. But outside of it, this is clearly a chondritic texture. So we haven't melted the whole sample. And if we melted the whole sample, then the entire sample would appear very dark.
Right.
And it would not appear like this. So that's why I went with a shock stage of 5. So we have
Very cool.
Yeah.
L6, S5.
I don't see a whole lot of S5s.
There's not too there's probably there's not too many of them, that's for sure. But there are several that are out there. I think that the problem with this scheme right here is when you start looking at like complex, like breccias or chondrites where you see these features in melt veins, but you don't see them outside of melt veins. And different people have different ways that they describe an S5 texture. Like for example, if I see maskelonite in the melt vein, but I don't see it in the meteorite, I'm not going to call it an S5, which is different than what this initial criteria was. So for example, this criteria says that if I see ringwoodite in a shock vein, the whole sample is S6. In some cases, if I see ringwoodite only in shock veins but not everywhere else, I might be hesitant to call it S6 because there are different opinions in the literature. So the bottom line is that different people might give a slightly different shock stage, plus or minus 1, depending on who does the analysis. But I tend to sort of follow recent research, but I also use this as like a overall guide.
If I can jump in for a second, Daniel,
Sure.
It's a very scientific process, but it does have a little bit of give and take, scientific, artistic expression, let's say. Now, chondrites, this is the easiest one. This is just a stony. There's not a whole lot of proof that you need for the NOMCOM, for the nomenclature committee. But I could see how a Martian augite basalt or an erg-chet or something weird, Albir Lalou, whatever it is, any achondrite that's weird and wild, anything that's ungrouped, or that's what your numbers show, and you're going to present it now to the NOMCOM. Now I think the group is kind of understanding or comprehending why it is submitted to the NOMCOM, and it could be either accepted, rejected, or rejected for more clarification.
Yeah, there's a lot of there's a lot of I guess there's a bit of the experience factor that kind of goes into this, but there's also a bit of the you know, every person who classifies a meteorite is going to have their own sort of touch on things on how they do this. Like I think we talked about a few years back about lumpers and splitters.
Yep.
And some people are going to look at something and, you know, see something like this, and they're going to just look at this and say, okay, you know, I see this texture everywhere. I'm going to lump it all the same. Where someone might, you know, they might say that not that we have it in this sample, but in another sample, like as an example, that some part of the meteorite might compositionally be a little different than the rest, but it might just be a very small part. But a splitter would probably say that that might be a different lithology, which you were talking about, Topher, that whether, you know, parts of the sample may be a different lithology. And I didn't see it in this sample from the areas I visited, but, you know, obviously I only visited certain sites, right? What if I visited this site right here and it had a slightly different composition? Or I visit this site right here. So there's a lot of thinking that goes into place that if I analyze representative areas of the sample and avoid all the weird and unusual areas like these melt veins or maybe some other parts, that will tell me what my sample is. And that's what most people who do a lot of lumping, or just people in general who classify, tend to do. But for certain meteorite groups, you might need to look at those unusual and different areas. Like if we're looking at a lunar meteorite, right? In my case, I look at all the lithic clasts because I study them for my research. But if I'm looking at a, you know, like an ordinary chondrite like this, I'm more focused on trying to get representative areas. So this is where you might have, at least maybe for some achondrites and maybe for some chondrites too, a slight difference in the classification that might take place between two people, where someone might say it's an L5, someone might say it's an L5 to 6, and someone might say it's an L6. And someone might say there's a shock stage of 4, someone might say 5, someone might say 6, right? So there is some variability in there. But overall, I don't think it takes away from what the sample is, and that is a highly equilibrated L chondrite.
Yeah, I agree. I do have a question for you about you were getting into the high pressure. What are they called? Not photomorphs. The
Polymorphs, yes.
polymorphs. Thank you. And for our submission, that's not really a key important data point that you're going to necessarily pass along. You excluded it in some of our readings, but I have a question regarding our good friend Vince, who likes studying high pressure polymorphs.
Yeah.
How do you, as a scientist, not handicap another scientist who wants to study those when it's not important to you and your classification?
So that's a great point that you made, Topher. So clearly, this is where the petrography section is extremely important in the Meteoritical Bulletin database. So, for example, I'm not going to, you know, list the chemical compositions of any of these potential high pressure polymorph phases in here. I can't really guarantee it without a different kind of analysis. But what I can say at least is within several shock melt veins, or within a shock melt vein, you know, several minerals or several grains were observed that potentially, you know, matched with X high pressure polymorph. So I could say within a few shock melt veins, a mineral phase that was chemically consistent with something like a majorite garnet was observed. But I wouldn't give the composition of it because I'm not very certain on that. And I wouldn't specifically say that it definitively is there, but I would imply that it may be there. So if someone is interested in shock melt veins and they want to see this particular meteorite and they say, oh, there might be this mineral in there, then this might be a sample they want to borrow for research. So it's important to have some descriptiveness in your petrography section for potential researchers if there's something that could be interesting to them. But if you aren't sure on something, you definitely don't want to say that you have something and then they borrow the sample from you and they do a lot of work and then it comes to find out you don't have it, right? So you want to make sure that you're understanding the limits of like what you can and, you know, can say or can't say on the petrography section.
Makes sense. Thank you.
And in the description, the bulk description of this rock, we're going to add in that it's got significant shock veins of such and such width, and that could be something that a researcher would search for in the METBUL.
Also, Daniel, this is a chance for us to get all these submission questions out of the way. Like, there are some METBUL entries that are so skeletal, it's kind of like, wow, did you actually pay for that? No. Then there's others that have a whole lot of detail, a whole lot of data, and this is going to be one of them. This is going to have a narrative, a story. It's going to have all of our inputs in there.
If your question pertains to why some classifications appear very long and some appear very short, or descriptions, there's a lot of factors that go into it. Obviously, if it's a fall, right, there's going to be a huge history section with that. There's going to be GPS coordinates, there's going to be recovery, potentially some stories in there. With if it's a equilibrated ordinary chondrite find from the Northwest Africa desert region, you're not really going to see too much because like I mentioned, most of these areas are very similar textures. Maybe there's going to be a sentence or two talking about something unusual you might find. Like I would probably say, in a melt vein, I observed what appeared to be this phase. But it really also depends on I guess, the amount of interest that the person doing the petrography also has. So if I'm heavily invested in lunar meteorites and I have a lot of research background in them, then I could probably see an image of some clasts. And maybe from reading those papers, I can go a little more detail on the petrography. Versus if I were to see something like a howardite, I am very familiar with the different types of eucrite diagenitic materials, where they may, what their compositions are. But I wouldn't know as much as someone who does research specifically on HEDs in my write-up to to add more that they may find useful for researchers, but not necessarily interesting for, just someone who just wants a classification done. So that, I say, comes down to, the relative amount of experience some people might have with some groups that they write more or want to write more versus other groups where they know enough to classify it, but they might not know everything about the research aspect of it to go more in detail. But some people also want to be very descriptive, when they, talk about different criteria. So some petrography sections I've seen have people where they report various chondrule textures that they observe. So like if they see porphyritic chondrules, barred chondrules, radiopyroxene. Some people like to report area percentages or modal proportions of different minerals. Like it's really depends on the person and the sample, I'd say.
Another thing was photos. A lot of classifiers don't submit photos. Historically, they haven't really been included in METBUL submissions. So we're always striving to, when we classify stuff, have pictures to go with them. Is that something you do as a classifier as well, to load the pictures into the classification rather than rely on other people to submit after the fact, and it has that caveat, these pictures aren't guaranteed, blah, blah, blah?
Yeah, that's a great point. So the thing is that there's two ways you can submit to the Meteoritical Bulletin submission form. The first is you email it to the Meteoritical Bulletin database editor, and you attach the spreadsheet as like an attachment. But then you can also attach photographs as well. The other approach that I do is if you're a frequent submitter, there's actually specific links that you go to and you just upload your form there. But when you do that secondary approach, you can't add photos initially. You have to wait for the editor to upload it. And then if the sample isn't approved immediately, you can add pictures, but in most L5, L6s, equilibrated chondrites, they're approved like almost instantaneously. So it doesn't give you the chance to add photos at that moment. But what we could do is we could do the email approach where we include, a few photographs and the submission form, and we email it together to the Meteoritical Bulletin database editor. And yeah, you can include photos on there. But I have been told by a few people on the committee not to have more than 3 photos.
Gotcha.
Because for some reason, having too many photos, I've just been told is not like something that they like. So if there's 3 or 4 really good photos that you want to have initially, like when we first submit it, we can put those. But later on, if anyone, I guess, wants to add photos later, they can always. I imagine there's There's other ways you can upload photos after a sample's already been in the
Yeah,
database,
there
but
is.
yeah. So you can do that approach also.
Yeah, I just like because a lot of my media creation, I need to have an authenticated photo
Yeah,
of something.
yeah.
So it's real important for me. I just can't take someone's word for it that that's what it is. I want the nomenclature committee to have it as part of the submission process, and there's no doubt about it. When I put that picture in my media or my education, whatever, I know it's legit.
Yeah, absolutely. We can definitely include, some of the important photos in there.
Yeah, it's not really important in this case necessarily. It's an L6, you know what I mean? But yeah,
Yeah,
it's nice to have the main mass photo at least in there, and then
sure.
everyone can submit their slices individually.
One more point that Topher touched on there that I think is important here too is that a lot of the classifiers will get by with the absolute minimum sample size, like looking at the areas of the olivine or looking at the areas of the low calcium pyroxene. And Daniel's classifications they're at in the top tier, the number of data points and just overall accuracy and attention to detail there, and not about it's about describing the meteorite, not about the absolute minimum to get classified.
Well, he hasn't been doing it for 65 years. He's not disgruntled yet.
Well, I will say that it's also a large part of it is the technique that's used. When you're using, if you have 3 hours to classify a sample and you're using an electron, microscope with the EDS detectors, you can get data points a lot faster, as we saw in part one, where we're just clicking and getting points. When you're using a microprobe to get data points, it's a lot slower, right? You spend several minutes on one point, and navigating throughout the sample takes a lot more time. And so, you might see some samples analyzed with the microprobe have like 5 or 6 olivines, but it might also take the same amount of time for them to get 6 olivines as it would take us to get like 15. But the data on the microprobe is slightly more precise. It's more quantitative, more useful for things like research, and of course, the resolution on the data is a lot cleaner than with our technique, right? There are limitations with the EDS, but we get so many data points that you know that it kind of almost equalizes out. That maybe not every data point is going to be exactly the correct composition. Maybe the phalite is actually 20.3 and we're slightly off it a little bit, but if we get 20 more data points and we average it, maybe our average is closer to what it should be. Or at least we know that it's more consistent throughout the whole sample. So this just goes back to, different techniques to classify have different pros and cons. And the benefit of the technique we use is that we can go to a lot more areas in the sample in the same amount of time as another technique. But if I'm looking at like a very specific kind of meteorite where I need to get a certain value that needs to be exactly, this number, for some ungrouped A chondrite or something, then, this technique might not be as helpful versus using a probe if I just need a very specific number and I can get away with a few data points. So it really depends on the technique.
Mhm.
Okay, so the final thing here, so we have the shock stage, the petrologic type, and the meteorite group is this weathering scale. And this is kind of very basic. Again, you normally would look at a thin section under the polarizing microscope in reflected light. That's the ideal way to do it. And I did it, and I got a weathering grade of about, I believe it was 3, uh, possibly 2. It was somewhere in the middle. Normally, your weathering grade's plus or minus 1, because different parts of your sample might be, weathered to different extents, as you showed Topher in your photo, that some parts are more weathered than others. So, you might be more of a W3 when you're looking at one thin section, and maybe another one's like a 2. But overall, it's moderately weathered, your sample. And we can also check this if we just look at, you can either look at the hand specimen and you can look at the metal and see like how much of that metal looks clean, how much of it looks, altered. We're definitely not W4 plus, because if we were at a W4, then that means that all of this, well, let me see if I can find that means all of this troilite right here and all of this metal would essentially, just be altered, and it wouldn't look as clean as some of these grains do. So we're clearly not there yet. And even here, you can see in this metal right here, if I just zoom in right there, this is alteration that's taking place in the metal. So it's giving off this color, but this metal is clean. And another way to show it is this, where this is clean metal, this is some alteration to iron hydroxides, but not all of it has been altered. So we're definitely not W4, and we're probably between a W2 and a W3. So I went with W3, but someone else who classifies it might say W2, but it's moderately weathered.
L6, S5, W3.
Yep.
Bingo.
So pretty much we've looked at all of the areas in your sample, and I would classify this as an L6 chondrite, highly shocked, moderately weathered. And this would be my classification of your sample. So this is the data processing stage, and now that we know what your sample is, all we have to do now is assemble the MEPL submission form.
And a little commentary here, there was a bet going, and I think Topper was the one who rang the bell or grabbed the golden ring off the carousel.
Yep. I was right on everything for the first time in my life.
And if everyone is ready, I can start getting into the submission process. Now, for this submission part, this is going to be very interactive. So, discussion would be great during this part. We're basically going to take all of the different sections of, of our submission form, which include history, physical characteristics, mass holders, all of the stuff that I got when I was doing the data processing. And so if anyone wants to discuss anything, or if anyone feels that maybe we could add a few things to a section, feel free to mention it. But with that, I'm just going to just share what the submission form looks like. So this is it. It's a very basic Excel spreadsheet, right? This is what classifiers use to submit your samples to the Meteoritical Bulletin database. And I can talk a little bit about each of the columns, but they're all in the MEPL. So proposed name, the name that we assigned to it, what country it was, a little more locations about the site. If it was found, you'd list the date, and if it was purchased, you'd list where it was purchased and when. If you have GPS coordinates, you put those in. This is total known weight, number of pieces. This is the classification you assign to it. Shock stage and weathering grade. These are the summarized olivine and pyroxene compositions. If you're measuring magnetic susceptibility, you put it here. Here you put the name of the classifier, so I filled that out already. Classification method. This is if you have the option if you want to list your, what technique you use, but really it's only used for like if you're doing a very specific method. So you might see some people classify ordinary chondrites just using magnetic susceptibility, in which case you'd put it here. Type specimen mass, I filled it out. This is the gram number of what we have. So we have about 214 grams here. This is our type specimen repository location. This is Cascadia. That's what we're listed at. The main mass location would be who has the main mass. The finder would just list the person who discovered the meteorite or the number of people who have. Now this section is very important. This is comments. So if there's anything else that you want to say in here in that isn't relevant to a particular section, you list it here. So if we want to, list something like anything relevant to the channel, meteorite education, something for promoting outreach, we could list it here. You could also put it in the history section, or we can kind of fit some of it here and some of it here. So we can discuss that as we're filling this out. This is history. This is physical characteristics. So these two sections, I'll definitely need the help of everyone to get these filled out with. These two sections are the ones that I fill out from that other form with the data I got and what meteorite group it is. This is just saying what my overall classification is. And then this is a very important section. This says who owns what. So basically, I'll have to put who owns how many grams for all the mass holders on here. And the final section says submitter, so I'm just submitting the form. So in the physical, we're just describing that stone itself. For example, you can say it's partially crusted. You could say that there's parts of it that show a sharp, sort of break that likely indicated this was some part of a fragment of something much larger. You could definitely say that in there, but you have to. All of this is referencing that particular stone. So we're just describing.
Okay.
So from that stone, what are some of the things we see about it that are worth mentioning? So you definitely could mention like external characteristics like fusion crust, color, and you could mention obviously, Pat, that it has an uneven surface to it. Sometimes the nomcom isn't a big fan of speculations that this could come from something much larger, but we could say
Okay.
that in this case. I don't think it's too. I think we all can agree that this definitely came from something much larger, right? It's definitely
Okay.
a fragment of something larger, but the way you report it has to, fit with the context. So far, that's pretty good. So we talk about the veins that we see throughout the sample, the weathering features, and the sandblasted or sand polished fusion crust exterior.
The uncrusted parts, are a brownish color, and the fusion crust sort of between black and brown.
Okay, so let's start from here. So we're going to give it an NWA name. So country just means where it was found or reported to be found. So is there a specific country like Algeria, Morocco, or is it just
It's Northwest Africa.
Okay, all right, so we'll go with that.
We purchased it in late January of 2025. It was probably found in 2024, but we do not have any proof of that.
So January 2025. And where did you purchase this at?
At the 2025 Tucson, Rock, Gem, and Mineral Show.
Okay,
And it
so
was purchased from Mohammed Hamani.
okay, so that the location exactly and who it was purchased from, that'll go in the history. The place just refers to the city. So we'll
Okay.
Okay, so what is the total known mass?
9,580 grams.
Okay, all right, and it was a single stone, L6, S5, W3. All right, so my average is 25.3 plus or minus 0.4. Okay, so phalight's done. Frostlight, I'm just going to do the same thing very quickly. Okay, so 21.4 plus or minus 0.3. So that's the average for frostlight. And then let me just quickly get the average last night, 1.5 plus or minus 0.2. Okay, so Sue, so for the main mass location, how do you want me to say? Do you want me to say Topher spin meteorites? Do you want me to say Topher spinato and Sue spinato? How do you want me to?
Actually, if you could put Sue Spinato from the Knowledge Bolide crew, that would be even better. I think I put that note in the spreadsheet. Like, we're trying to get that Knowledge Bolide name out there. Just
Let
because it's
me-
more about education rather than selling.
Gotcha. So the history section. Okay, so this is sort of the big one here.
Could we get away with stating in the write-up history that that these videos exist? That there's 3 videos of the full open kimono on the classification process?
Great question. Yeah, we can try to put that in there. I'm trying to think from the perspective of wanting to put it in, but also trying to think what Nomcom would not want to have, or like what they would do when they see this. So it in a way that flows. I'd like to keep honestly, I'd like to keep all of this in here. I'm just trying to see whether some could be moved to the comments, so maybe we won't get any complaints that the history section might be like too long or something like that.
It's a kind of a compelling story.
Yeah, I think so.
It's not really been done before.
It was funny, Topper and I were talking about that, and we're like, well, we certainly bet that there are groups of people that may have gone in on a rock, but none of those groups have documented it with the classifier to the stars like we did for video and for people to learn from for, ages.
Yeah, and it's it's hard to tease apart the commercial part of it versus the education part. Yeah, there you go.
Yeah.
That looks great. That looks great, Daniel.
So, what do you think about adding this in there?
There's absolutely no selling on that particular on all three of these. This is pure education that I have never seen on YouTube. The entire classification process is new territory I'm sure you can search through YouTube and you won't really see anything like this.
The 9,500 800-gram single stone purchased in late January at the 2025 Tucson Rock, Gem, and Mineral Show by Sue Spinato of Topper Spin Meteorites from Muhammad Hamani became the focus of a highly interactive project for the Knowledge Bolide crew, where Daniel Sheikh created the opportunity for crew members to participate in a meaningful hands-on activity to gather data from the meteorite using the scanning electron microscope, resulting in an engaging educational experience for transparent meteorite classification made available to the entire meteorite community at a well-attended online event. And then in parentheses, documented on video in a 3-part video series available online on the Topher Spin Meteorites YouTube channel in the group classification playlist. 13 crew members earned recognition in this classification, including for 4 first-timers, highlighting the crew's mission founded in 2020 by Topher Spinato to advance meteorite science through teamwork, mentorship, and discovery.
Yeah, that sounds great, Daniel.
Okay, all right, so we will keep this. So pretty much all we're putting in the geochemistry section is the olivine and the low calcium pyroxene compositions. And that's just, again, the phthalate, peroxide were last night. So the way it's typically requested is you do something like this. You put phthalate. So you want to report the average, standard deviation, maximum, and minimum, and then the number of grains. So the important thing when you're doing the geochemistry section is there's a specific order that you want to put things in. So the olivine phthalate's this first part right here. So it's going to be 25.3 plus or minus 0.4, and then you want to put the range. So this is looking at the minimum and maximum values. So that's going to be 24.7, 26.2. And then you want to put the number of grains. So that's going to be what this N means, 24. So that part's complete. And then the low calcium pyroxene, we're just looking at peroxide. So peroxide, 21.4 plus or minus 0.3. Very important here, if someone watching this in the future is going to classify and submit a meteorite, don't put a space between ferrocite and wollastonite. The committee likes it where you keep that all in one area. So that would be like this. And then same thing, we have the range. That's going to be 28.9 to 23.3. One of the things you learn very quickly when you classify meteorites is that you become very good at using Microsoft Excel. So that was a fun thing. Okay, so that section is done, and so we don't need this chemical data anymore. So we have the geochem, and I always check just to make sure that this matches with that, because sometimes if they're different, you could get a comment about it. So this looks the same, this looks the same, and that looks the same. Okay, so we're good here. So first we have to start with how many grams we have in the repository. So we have 214.5 grams. And then now we need to list each mass holder. So yeah, so first usually in some cases they like the main mass holder at the end, but it doesn't matter too much. So okay, so how much we have at the repository, main mass, and then the additional specimen holders, then we can just list everyone in here. Okay, I think we got everything here. So now we get to the write-up petrography section. So usually what I do is, because this is an equilibrated ordinary chondrite, I usually say just a brief description. So the first sentence is just an overall description of the sample. So I always say sample represents an equilibrated containing the feldspar grain size, which is very important for that L6 specific petrologic type. So secondary recrystallized feldspar. And the reason why we call it, in case anyone's wondering why we call it secondary recrystallized, it's because the feldspar formed secondary to when this on the initial parent body, when this this meteorite was initially on. So when you form these, for example, this is an L6. So you can say originally, when you accreted and you formed this material, it was primitive. So like 3.00, type primitive, but then through later heating, primarily driven by, thermal metamorphism on the parent body, you begin to form this secondary feldspar, which the reason it forms is because your chondral mesostasis actually decomposes and you turn into feldspar and high calcium pyroxene as a result of it. And the reason it's called recrystallized is just because in typical metamorphic petrology or in general, whenever you're forming new mineral phases from pre-existing ones by adding heat, some people call that process like static recrystallization and grain growth. Uh, you know, it's just a term that's been used in the literature. But this just basically means this is feldspar that we only find in our equilibrated ordinary chondrites. And here I'm also listing the accessory phases. So Art asked earlier about reporting the phases that we observed. So we observed iron, nickel, metal. We observed troilite. We observed chromite. And we observed calcium phosphates. So this could be a mix of things like chlorapatite or marlite, but here I'm just saying that they're both calcium phosphates. Yeah, this is kind of the research sentence is like if you see anything
Yeah,
very interesting in this sample that you want to put on
right.
there.
And
So
and with each of these fields that are in the Meteoritical Bulletin, you can do text searches on words or phrases or what have you. And so somebody that was interested in garnet phases could find that entry by searching for garnet.
yep, absolutely. So this is how they like you reporting it. So you save it as this, and then now once it's saved, the last thing to do is we just write an email to the MetBull editor. So I can tag Sue and Topher both in that email. But basically, at this point, we're all ready to go. This email just gets sent out. We're saying that this is our submission, and any photographs that you want me to include, please send them to me, about 3 to 4. And yeah, that's pretty much it.
Woohoo!
Awesome.
Daniel, thank you very much for spending the time with us and going through all of this. This is super, super valuable for me to see like Topher says, see the sausage being made.
My head is spinning from how much you have to do this. And every little number you're putting in and inputting, double checking, and my hat's off to you. I don't know how you do that. I mean, you've done this over 300 times. That's amazing.
Thank you. Yes, so if you add up all three, I mean, obviously there was a lot of talking, I imagine, but if you add up all three parts together, yeah, the classification process takes quite a while for any classifier for samples. So if a sample takes several months to a year to go in the database, sometimes there really is a lot of work that we do behind the scenes. So I hope
Yeah.
this whole process kind of sheds light on like how all of the classifiers like have to go with going from one part to another and sort of trying to figure out what the sample is, and it does take time. Like I have a lot of packages here that I have to open and then take samples out, put them in the repository, ship stuff out for thin sections. I have to wait on them to come back. We have to coat the thin sections, as you remember, we have to carbon coat them, and then you have to schedule analysis and things like that. So for me, my constant thing is half of my brain is on my research, and then the other half is all classification. So I have to shift between them both all the time because there's a lot of work with managing a lot of Facebook messages from a lot of people and memorizing who sent you what sample and everything. So
Oh
yeah.
yeah, we feel your pain for sure. Oh my goodness.
Daniel, thanks for your time. That was really exceptional, truly. It's very impressive the amount of work that goes into it and the detail you adhere to. It's fantastic.
Thank you, Boris. I really appreciate that.
Don't know how much is that is going to make it public and how much is going to make it members and how much is not going to make it at all. But I can tell you this, the crew is strong and the crew is wise. Even when I'm in pain and I can't sit for a second longer and I have to tap out, the crew takes over. my loving wife takes over, and Daniel was generous with his time. So thank you very much. I really appreciate everyone in this group classification. It's an amazing project, and I'm really glad to be a part of it. So Daniel, thank you very much for your time. Really appreciate it.
Yeah, no problem, Topher. Like I said, always happy to help contribute. And, it's a symbiotic relationship that we all have, meteorite collectors and scientists should have.